got 2 talks today. We've got Adam and then we've got James. Oh, back there. Both Adam and James have done multiple talks for us, so it's great to have them back again. And I know a few people here have said they'd love to give a talk as well, so just feel free to grab me at some point. Next event will probably be in January. We'll take a break in December. And yeah, as always, I've got this set up because we'll record the video. I'll upload them on YouTube within a week. So we'll have Adam on, and we'll have like 5 minutes, and we'll have James on. So some pizza and some drinks as well, so feel free to grab yourself a drink whenever you want. And obviously, big thanks to BJSS as well for sponsoring the event and allowing us to use this like beautiful space. So yeah, thank you to you guys, and yeah, I'll pass you over to Adam. Thank you.
Thanks, Kasim. It's nice to see some familiar faces in the crowd as well as some new ones. So for those who have seen me talk before, thank you for coming back and subjecting yourself to this again. And for those who's a first time talk, you know, again, thanks for coming and bothering to listen to me. So yeah, today I'm going to be giving a very small introduction to compilers, and it's all going to be done in C#, which hopefully, touch wood, most of you here are familiar with, given it's a .NET event. But I should probably start off by telling you who I am, because I am just some strange individual who's stood up here talking away. So my name's Adam Parker. I've been doing development probably for the last 7.5 years, give or take. The majority of that has been in .NET and C#. And so, you know, you can usually find me online for using the grab-a-byte handle, and you'll probably see this little gopher mascot sitting around as well. So if you see that, it's probably me. But yeah, so a bit quick overview of what the layout of this is going to be. We're going to be talking about why compilers, you know, sort of why you should be listening to it, you know, why it seems like compilers can be a really difficult thing. Then we're going to go through all of the different stages of what a compiler sort of does under the hood. So you've got lexing or tokenization, parsing, the actual compiling part of it, and running it through virtual machines or other means like that. And then at the end, there's just some extra resources, just in case anybody gets interested in this kind of thing, that you can go away and take a look at. So to start off with, why compilers? And the first thing for me is that it's just really interesting when you think about what a compiler is actually doing, the fact that all of us are able to sit there and write some high-level code that looks like English, that can read like English, and somehow you get a little machine that's a bit of silicon to just run it, and it just produces this output that you like. Like, that is really fascinating, really, really, really interesting. Secondly, it's really nerdy as well, because you can get really low level with some of this stuff, and you can get into bytes, and you can, like, you know, like, when was the last time anybody here actually had to deal with bytes? Like genuine manual bytes, and that can actually be really, really fun to sort of go back to those basics and right back to those low level areas. Again, as I just mentioned, it can be low level dealing with bytes, and you know, a lot of people will say, oh, in order to write a compiler, you need to write in C or C++ or assembly or whatever, and these really low level languages. Spoiler, that is not true at all. But you know, it's one of those things that a lot of people will think of. And the final one is that it's a tool that we use every single day. And I'm actually a firm believer of the fact that if you use a tool, you should probably know more or less what it's doing under the hood, because that allows you to actually be able to appreciate the niceties of what the tool that you're using is doing under the hood and the work that you're getting away from. And also it means that sometimes if things do start to go a bit awry and a bit wrong, you have that ability to go, well, under the hood it's doing this, so there could be a problem here. And most of us will probably use that tool through something like .NET Build on the command line or through Visual Studio or something like that. But what you might not actually know is that under the hood, Visual Studio, and that will call the likes of csc.exe, fsc.exe, and vb.exe, which stands for the C# compiler, the F# compiler, and the Visual Basic compiler. As you can see in the compiler space, people like things to be very terse, so you get these 3-letter compiler things. But that's just that. But yeah, they're what's actually been run under the hood, and that's where a lot of the guts of what happens when you build your project happens. But another part of it is, one of the reasons why like compilers seems like this really, really difficult thing to do and whatnot is because if you start taking a look online, you Google, oh, how do I build a compiler? What you'll be greeted with is probably something that looks like this. It is literally called the Dragon Book online for compilers and whatnot, and it's like, you know, like if you take a look at that book, you start to think like, oh God, how much is in this? There's this big scary thing, and you know, they're literally battling dragons and whatnot. And you know, the other thing is that like like if you take a look at the dates at the bottom there, 1977 is when the first edition of this book was written. In 2006, it was rejuvenated for a second edition, which just added a little bit more on there. But like, you know, these are concepts and things that have been going back way back when and whatnot. And so, you know, back then people would have been using languages such as C, or if you're really fancy, C++, which thank God that programming languages don't have copyright law, because I don't know if you can tell the similarities there. But you know, like as I say, like these concepts and these ideas and whatnot have gone back all this time. Right? C and C++ themselves go back 1973, 1983, and so these really low-level things and these concepts from all the way back then. And so a lot of people look at this and go, well, clearly I don't know enough because I've only ever programmed in JavaScript or C# or, you know, insert your favorite language here. And everybody seems to think that this is the case, and it's really, really not. And to sort of give a little bit further, there's a small history lesson here, which is, does anyone know why it's actually called C? Pretty much, bang on, yeah. Exactly, there's a programming language called B. Programmers really aren't that inventive. There is actually a programming language called D now too, so I'm expecting by the time I retire I might be at F. We'll see how that one goes.
I think there's also a Z.
Is there over a Z? Oh, okay. Somebody skipped the rest of the alphabet. Honestly, that's just not on. That is not on.
Like Excel.
Yeah. But anyway, the B programming language was written by a guy called Ken Thompson. And if that name sounds familiar to you, right, it may sound familiar for all of the work that he did way back when, but if you go to look more recently, and keeping within this sort of programming language and compiler space, anyone recognize this little programming language that seems to have taken the world by storm? In November 2009, so B was written in 1969, and in 2009 he's still making programming languages. So this guy's been doing this thing for 40 blooming years. And it's like, you know, there's this thing of like, well, if this guy's been doing it that long, and he was there back when compilers were still being written in C and learning all this bytes and all that kind of stuff, like, what chance do we have of learning how all this stuff works? And of course, you know, it's one of those things that all these things together can make compilers seem really scary and really difficult to learn. But that's not really the case. So what we've got here is we've got these different steps. You have your source code. That's what you and I write on a daily basis, you know, C#, Java, and so on. And that gets passed through a part of the program called Alexa in a process called lexical analysis. You might also hear it called a tokenizer. That gives you a list of tokens. That goes through a parser that gives you an abstract syntax tree. We'll get more into what that actually looks like and what that means when we get that slide. And at this point, you can kind of go one of two ways. You can either go the way that we go there and go and push it through a compiler, or what you might also see is that people will just actually interpret that tree. So if you think of the likes of Python and whatnot, it just reads it, parses it, pushes it through. Some people will also shoot me for that one because it's not 100% what's happening, but it's an easier way to think about it at a high level. So that goes through a compiler. We produce some bytecode. Or if you're feeling really fancy, you can go to machine code like direct, x86, ARM, and so on and whatnot. You know, if you've ever done any like lower level languages, you might find that they produce executables or ELF files or something else like that and whatnot. In our case, we're going to be compiling to a bytecode because it's a hell of a lot easier and you don't have to learn assembly at that point. And then that goes through some sort of virtual machine and you are able to now execute your code. So that's the steps, and that's kind of the high-level overview as to why on earth you need those particular steps. So first thing is this lexing and tokenization. And the idea behind this is you have some sort of unformatted string like this. In this case, you know, we're just going to be dealing with mathematical expressions. Okay? So you have some sort of string like this. It's just a bunch of characters, and there is absolutely no meaning to it, and you want to be able to split it up into the individual parts that we probably read it as. You know, you probably look at that and you're able to identify, well, that's definitely a number 1, that's a plus symbol, that's a 2, and so on and so on. You break it up into those individual parts. And if these were multiple numbers, say that was 123 at the start, you look at that and you go, that's 123. And that is the start one, and you take that as one thing. So the first part is to try and break it up into these individual pieces like this and whatnot. So what we're aiming to get from is from the left-hand side to something that looks like the right-hand side. And a lot of you might look at that and go, well, that's easy. Just split it on the white space. And the problem with that is, as everybody here probably knows, you cannot trust your user at all. Your user will try and mess with you. You know, that first one, there's no white space, it's not going to work. That second one, it's actually, you know, you have a question there. Is that actually two separate things, or is there just like 10 white spaces in the middle, you know? And so it seems to get into these weird territories like this and whatnot. And so, you know, just in the same way that we all have to deal with whether the user tries to do a SQL injection attack through a web form or something, compilers have to deal with the fact that we as users are going to write code that is just quite frankly wrong, weird, or something like that, whatever you want to call it. So how do you get around this? The idea behind this is basically you're trying to create these little things called tokens, okay? And so for every token that we have some sort of type of token, and we have some sort of literal. That's all we've got in this one, but you could also imagine attaching things like the character position or the line number and things like this for, you know, tracking where in the source code it is for nice handy error messages. Spoiler alert, there's no error handling in this whatsoever. So none of that stuff's on there. And so going on from that, basically, don't know if that's going to be a bit too small for some people to see in the back. If it is, I apologize, I've made it as large as I could on the screen there, but that right there is effectively the entirety of the code for being able to create these tokens. And effectively what it's doing is you're going to the first character and you're going, okay, well, what is this character? And if we manage to find either the star, the minus, the slash, or the plus, then we can just go, okay, fine, we know exactly what it is, and we can take it. If we don't find any of those, then we have to go, okay, well, let's just keep reading along. Let's keep trying to find numbers. You know, in this case, we're doing decimals, so you'll see at the bottom there, it's take while it's a number or it's a decimal point. And so it's like, you know, we're going to go through and we're just going to keep reading until we get to the point where we're not looking at one of those, and then we know we finished looking at the number. And then it basically takes that and skips forward that and continues to do the same thing over again. And again, we're just going to be skipping over white space. You'll see the skip white space method there. And that's for, you know, if you put like 1 space plus space 2 and so on, you know, you can parse that one, that's a number. You need to skip that white space to know what it is that you're getting next. So that's effectively what's going on in the code there. For anyone who's actually curious, can anyone spot the bug in this? There is a bug in this because I tried to make it as short as I possibly could in order to get it to fit on one slide. Give anyone a second? If not, that is going to be deemed a valid number in this. Just ignore that. That's a bug, but you know, you can start to see the part where, you know, some of the compiler writers and stuff, you know, you have to defensively program against this kind of thing, and that's just kind of just in take while it's a number or a dot. I haven't counted how many dots there are or anything like that. But you know, you can already start to see, even in the first phase of this sort of big chain of pipeline, there are already places where you have to defensively program against what a user is going to hand you. But ignoring that, we pass it through, and lo and behold, we take that little expression we had at the start, and we end up with these tokens that we now have that we can use. Does anyone have any questions at this point so far? No? Awesome. Great. So the next stage of all of this is parsing. Ooh, there we go. And so the idea behind this bit is we have that stream of tokens that we've been given, or an array of tokens and so on. And basically we want to turn that into something that actually mimics the structure of what the code is, you know? So right now it's just a big long list. We have no idea what any of that actually means. There's no structure, there's no priority. It's just a big soup of nothing. And going left to right doesn't necessarily always work. So I'll give a quick example. So we've got that, so we go left to right and we go, okay, we have 1 and we go plus and we go 2, that bit's fine. And then you go to the next one, you go, okay, well 1 plus 2, and then we do minus, and then it's going to be 3 on the right. And I think this one is correct if I remember my BODMAS. Yeah, so you have to do the addition before the subtraction. And then you go to the next one, and this is where things start to go a bit awry, because that's not right if you think about like BODMAS. So BOD, so division should have been done first, and you can see very clearly that that's not going to be the case. And so again, you end up with this problem where just going left to right and just trying to build up this tree doesn't work at all, right? So I'll go to the next one. So that's what we're actually expecting to get, and that is what we got by doing it. And you can see at the top, I've added like the actual thing with all the brackets around it to show that priority. And like, obviously that one on the right looks very wrong. The one on the left is what we're expecting to get. So there's sort of this question of like, well, how do you make sure you get the tree correct? Okay, because this is like obviously a massive part of it. If you get this wrong, the whole thing's going to explode, or you're going to get some really weird behavior. So we're going to go through a little bit of an algorithm that's called top-down operator precedence parsing. You may also hear it called recursive descent parsing, or you may also hear it called a Pratt parser, which is my favorite. And it's got nothing to do with being a Pratt. It's because it was actually proposed by a guy called Vaughan Pratt way back when, and I forget the exact date. I think 1970 something, if I remember correctly, but don't quote me on that one. But you know, as I say, like in terms of this, it sounds really like big words and whatnot, but we all have an idea of what precedence is, and I've already sort of mentioned it in the talk. We all know about, well, that was supposed to have an animation, but we all know about BODMAS. We all get taught it at school with maths and whatnot, and we all follow that rule every time that we do it. For the sake of this talk, we're only dealing with the division, multiplication, addition, and subtraction, and that's just, again, to condense it down to try and get as much code on the slide as possible to be seen. But yeah, so like that's the idea of precedence, the idea that one thing should be done before something else. And so basically, we can use this to try and understand it. So if I go to the next slide here. So in the top right here, you'll notice that there's a little chart here. So we're going to start with the lowest precedence of 0, and everything up there is going to be given a new precedence number. So 1 for the subtraction, 2 for the addition, and so on. And this is what we're going to use to control how we build up that tree, okay? So for starters, we start with the lowest thing, and we come in and we say, right, oh, we need to parse this first token. What is it, and how do we deal with it? So we come in and we go, great. It's a number, it's 1, we know we can just parse a number. Job's a good one, great. So we'll take that and we'll put that to one side for the time bit. So we're currently at 0, right? We started at the lowest and we've just taken the first thing, so we're still at 0. So we take a look at the next thing in the tree and we go, hey, the next thing we need to look at is a plus symbol. Okay, so that's now a 2 because we need to do our addition there. And because that number is higher, we now need to continue to try and parse. We know how pluses are parsed. We have a left-hand side, we have a right-hand side, so we can continue. So the left-hand side going to be what it is that we've already picked up and parsed, in our case, the 1. And then on the right-hand side, well, we're going to start parsing again, because again, it might be a surprise, but recursive descent parser, we are recursively going to keep parsing these expressions with this precedence, and eventually at some point, the precedence is going to go, nope, you've gone far enough and come back out. Okay? So continuing through this example here, we have that plus and the 1 on the side. We're currently at 2 because we've had the plus. We're going to parse the next thing, which is the number. We go back to the next precedence on the minus, which is the 1. And because that precedence is lower, because subtraction is lower, we just go, nope, nothing more. That's it. There's nothing more here to parse. That's the end of it. So, okay, great. We've parsed the 2. We've hit the minus and we've said stop. So we've now got this structure here, which is fantastic. That is correct so far. And so what happens is, this bit now gets passed off to the side, and we basically pop back up. And so you go back up, because if you think about recursive, you kind of, you know, you're within a function, within a function, within a function. And as you pop back up, that precedence number goes back up with it at the start. So as soon as you go back, you end up back at 0. Okay, cool. So we've now got the left-hand side of this. We're back at 0. What do? Well, let's have a look at where we are again. We're back at minus. We're at minus, which is the 1. Guess what? It's higher. So again, we can find out how to parse a minus. What do? Again, we take left, we take the right-hand side, do that, and here we are. And then to top it off, obviously, finally, we just go, we parse the 3, there's literally nothing, we're at the end of our stream of tokens, and here we are. And that's your fantastic tree all done. Okay? So I do have the code here, so I'm going to quickly try and step through if I can. There we go. And get my, so in here, I go to the program, you see we've got that 1 plus 2 plus 3. So if I just debug this. So here we are, this is where we're starting. So this is starting just the default parse. We're going to just say, hey, can you parse this thing for me with the lowest precedence? And so that's then going to go, and I forget which button it is for, step into off the top of my head. There we go. And so we go, hey, what's the current token? How do we parse it? Great, we're going to go and take it, parse it. So you can see that left-hand side there. It's a bit small, but that is number literal with the number of 1. Cool. So we've parsed that bit, and so we step over, and we get the next thing. So that's going to be the 2, the plus. So the next precedence is add. So because it's, and I hit the wrong key there, my apologies. Bear with me. And so we hit the add. So because that one is higher, we're going to step in. We're going to say, hey, how do we parse the plus? We're going to pass that left-hand side, which is that number literal, into it. And then we're going to do the parsing. So in this case, if I step into this, you'll see here we get literal, precedence, parse it, and then we return. But you'll notice here, so there's that parse expression thing. That's where we're doing that recursive descent, and we're passing in that new precedence, and it's going to go around and go through, and so on. So yeah, this code is all up on GitHub, by the way, afterwards. So if anyone wants to go and play with it and have a bit of fun with it afterwards and try and add things and break it, be my guest. But yes, that's, you can sort of see there that idea of how the code's structured, how it's built up. You're just constantly parsing left and right. You're constantly calling the same function. It's going to be constantly recursing, and eventually you just pop all the way back out, get to the top, and you have the thing that you've parsed. So that's that. Does anyone have any questions at this point? Because I imagine that this one can be a bit of a brain twister to get your head around, and sometimes it does take a few things to go through. God knows it's taken me a while. I've read 3 books on this thing, and even now I still get confused sometimes. So, any questions? No? Awesome. In which case, I shall continue. So, the next part of this, if it's going to work, there we go, is the actual compiling part of it. So now we've got this structured tree of how our program looks and, you know, how it's supposed to be behaving. And now we need to find some way of taking that tree and actually turning it into some sort of set of instructions, right? So a lot of the time, this is usually the bytecode. So you can think of like Java. Java compiles to the JVM, and it's JVM bytecode, and then you pass JVM through there, or .NET intermediate language that you might have seen if you've been playing around at all and you have those tools available. And then that gets run through the .NET virtual machine, or .NET runtime, I suppose is probably the terms they use. And again, otherwise you can just put it down to whatever machine code you fancy. So the idea behind this part of it is you have some sort of set of operations that you have to target, you know. Again, you know, you think like, if you think of like machine code and stuff, it's going to be, I'm going to load it into registers and do all this stuff and then pass this code to make it add the 2 numbers. Or in the case of like, you know, .NET, it's usually pushing things onto a stack and popping them back off to do that kind of stuff. But you have a list of instructions that you can do. And so the idea is you want to take that tree. So in the small case of our example there in the bottom left, you can see it's going to be push 1, push 2, add them, push 3, and then subtract it. And that order may look a little bit weird because that is not the order in any way, shape, or form that we actually look at that set of that sort of string of numbers and that calculation. So that may seem a bit weird, but it'll make a bit more sense later on when we actually come to running this code and so on. But the idea here is obviously you have a set of instructions and you need to target it. And the way in which this can be a bit weird, I have every instruction here, every operation for add, minus, subtract, and division, but like you could imagine a world where you didn't have the multiplication, and what you need to admit is, I know that I'm trying to do 3 times 7, so I need to add 3 to itself 7 times continuously. And so you can get into these situations like that where there is no one-to-one translation. You have to try and figure your way around it. But in this case, for simplicity's sake, we have every instruction we could possibly need to get this working. So again, there's the code for all of that. And it's really quite simple at a sort of high level. You have this compile thing, it takes some sort of expression. If it's a number literal, then we're going to return push that number. If it's a negative, we're going to say, hey, compile the right-hand side of it, and then we're going to push the negation. Again, it seems weird to put that backwards, doesn't it? But it'll make sense in a bit. If it's an infix expression, so that's going to be our plus, minus, divide, and multiply, we're going to compile the left-hand side of it, we're going to compile the right-hand side of it, and then we're actually going to output depending on what's on there. You know, so add, subtract, divide, or multiply. And so again, you know, this might seem really sort of familiar because again, it's another recursive thing that's being passed down, just like we did with the parsing before. You'll find there's a lot of recursion in compilers because you are constantly trying to parse the same things over and over and over again. There are other ways to do it, but this is one of the common ways and one that's like easily human readable in comparison to some other methods that can seem a bit weird and are a lot more machine generated. That's that. So the next part of it is just running it, the virtual machine, as it were. So there's two types of virtual machine: a stack-based machine, which is what we're going to be showing off today, where you basically build up a stack and you pop things off the stack and then you create this thing, and you know, that's how your computations happen. They all happen on the stack, and it's great and it's fantastic and it's easy to understand. There is also another one, which is a register-based virtual machine. And that one kind of tries to more mimic what like your actual physical hardware is doing. So if you ever look at assembly thing, you might see registers that are named like RAX or RBX or so on, and then you have to put your two numbers into those registers and then say add. You can't just say, oh, just push it on, just add them for me, please. You know, and so those machines are designed to mimic the actual real hardware. For the sake of this talk, I'm going to implement a stack-based one for two reasons. One, it's easier to implement, and secondly, it leads to a lot shorter code, so I can actually show you the code. So there you go. That is the entire code for our virtual machine. Almost. Obviously, there's a lot hidden underneath that handle operation function, but basically, we just have a class. It's got a stack in it. Some people might call that cheating to use the stack that's built into .NET, but you know, who cares? That's their problem to deal with. We're going to use it because it's easy and it makes it simple. And then basically all we're going to do is, for every operation that we've done, we're going to just handle it. And again, it's very super simple. This is where it might start to make sense as to why we were looking to compile things in that seemingly weird order of left, right, operation, and so on. So on the right-hand side here, again, I apologize if it's a bit too small. But basically, if it's a push operation, we're going to push that number into our stack. If it's a subtraction or addition or multiply or divide, we're going to pop two numbers off the stack. We're going to do our thing and push it back onto the stack. And so this is how like a stack-based virtual machine works. Again, you know, as I say, it's just push things onto a stack, pop things off the stack, do something with them, push more things onto the stack, and you have this constant back and forth like this. You know, in this case, we're just pushing numbers, so it's really, really easy. In like real language implementations, you're going to be pushing things like objects and function calls and all this kind of stuff that can get really complicated and really convoluted and whatnot, and you have to try and design it in that way. But for our sake, it's really easy. We have a stack of floats and that's it. Really, really simple. So if we take that expression that we started with, and then we pass it through our lexer, our parser, and then our compiler, what we end up with is this set of instructions: push 1, push 2, add, push 3, push 4, divide, push 5, multiply, and then subtract. And so if you start to sort of work through this and sort of imagine being in the shoes of the virtual machine for a second, you end up with this. So this is our stack as we go through. And so, you know, again, we push 1, then we push 2, and now we add them. So we pop them off and we add them together. So you're now left with a single number on the stack. And now we're going to push 3 and 4 and then do a division that's going to pop those two off the stack and push it back on. And so on and so on. And eventually you get all the way through down this and you end up with a single number left on the stack, which turns out to be the answer. And as far as I can tell, by putting that little string into the Windows calculator, that is correct. If anybody can prove me wrong, then I'm very happy to hear it, and I'm very confused as to how on earth that's the case. But nonetheless, that's sort of the steps of a compiler and a virtual machine and so on. And you know, obviously this is a very, very simplified example. We're using a very small subset of the maths expressions. We're using a very simplified virtual machine with it, you know. And so this is a very simplified overview, and it's definitely a 100-foot high level view of it. You can get really into the weeds of these things if it interests you. But yeah, so that's that. Do I have any questions on anything that's been done so far? No? Awesome. So as I said before, in terms of missing features from this thing, obviously we didn't do brackets, we haven't done any other and things like that and so on, or we haven't done any errors either. There is no error handling in here. You make a mistake in your expression, it will just explode, and that's just what it is. But you know, I was talking about sort of attaching things to the tokens before, like the line number and so on, and it's by bringing in that extra information during those steps that you can look at your editor and you can get an error message that says something like, cannot find foo on bar at line 42, character 7, you know, and obviously that information is propagated through the pipeline to the position that it needs to be. Most of that's probably thrown out when it gets to the point of compiling, because if you're running it, then it's going to be a runtime exception, and that's going to be handled at that point. But for the process of, like, you know, sometimes people will say compiler front ends and compiler back ends. The front end being lexing and parsing and making sure that it's structurally sound and whatnot, and the back end being, hey, go and generate the code and so on. For the front end, that side's very, very useful. That's how you get your error messages. That's where you get to see where the structure's incorrect and so on. And then on the back end, it's not needed at all, so it can just get thrown away. And obviously it makes for your code to be a bit faster as well, because you're not having to lug around all this information with you as well. There's also other things that you can have a look into. So in this case, we just sort of went literally straight through the basic pipeline, but there can be a lot more steps involved as well. So one of them would be like lowering. So like the example I gave before of if you didn't have the multiply instruction, having to do the add continuously to get to the answer, instead of just being able to do it once. You know, an example that some people might be familiar with this is if you've used like the recent switch expressions in C#. I guess have most people here used them, I hope, fingers crossed. If not, I apologize, but you know, you can imagine those things just being compiled to like an if statement under the hood. If this, return that, if this, return that, and so on. And one of the benefits of this is as a virtual machine sort of implementer, or even at the hardware level, you know, for some of these things, you only need to worry about optimizing one path. If you take that switch expression and you compile it down to a bunch of if statements, well, guess what? You now only need to optimize your if handling code, and everything else is faster, including your new fancy switch expression that's in the language. And another one that's in here, any optimizations. So the example I've got here is constant folding. Haven't done it for this one because constant folding would literally defeat the entire purpose of this. But that's like, you know, imagine you have two strings, const A called, which is foo, and const B that says bar, and then somewhere in the code you say A plus B, and it's going to be foo bar. And at compile time, we can look at that and go, well, that's constant, it's never going to change, we're going to smash them together, and rather than doing A plus B every time we need to look at this new variable, we're just going to slap foo bar in there and it's done. You know, you don't need to worry about it, and you'll see this a lot with like mathematical expressions. So if you imagine doing some complicated maths in your code, and there's lots of numbers and whatnot, you may do that for the sake of like being able to look at a formula and go, yes, that formula is correct. But in the compiler, if it can just go, oh, well, that just goes, you know, instead of doing A, B, C, D, it's, oh, well, that's just that times by 0.5. That's a hell of a lot less work for your program to do, and it's a lot quicker as well. So yeah. In terms of any additional resources, in case any of this has sort of scratched your itch in terms of compilers and what's going on, the top one is actually the paper that I mentioned, is done by Vaughan Pratt on the parsing algorithm. You don't necessarily need to read that. It's just there for thingy, and it is free, available on GitHub at tdop.github. Crafting Interpreters is a fantastic book. That actually takes you through 2 implementations. It takes you through like a tree walking interpreter kind of way, sort of similar like the Python that I mentioned before, and then it takes you through another level as well, which is to compile down to bytecode, but that actually goes and implements like a proper language. And you can read it completely for free at craftinginterpreters.com. You know, fantastic resource, huge shout out to the guy. So if this scratches your wrist, go give it a read, have fun implementing it, do it in whatever language you want and so on. I would highly recommend though, if you do that and you actually get some, some use out of that, go buy a physical copy of the book, support the author. You know, it's a hell of a lot of work to have written it and so on. And other ones that are maybe a bit simpler as well, writing an interpreter in Go or writing a compiler in Go, a couple of books by a guy called Thorsten Ball. We may not be Go programmers, but the Go programming language is very, very, very simple. And so those books are fantastic because the code that you get out is very, very readable and very simple, but you get a full interpreter and compiler out of it at the end as well. So it makes it easier to read through and understand what's going on versus some, crafting interpreters. The first one's done in Java, which is probably fine. The second one's done in C, and there are times that you will sit there reading going, I have no idea what's going on, because C is a wacky language at times, and it can be weird. And then just a couple of final ones there. Mermaid.live, that's how I did all the charts for the precedent stuff, if you want to look at that. All the code screenshots are done with this carbon.now. If you're curious about me, I'm at blog.grubbyte.dev, as well as being Grubbyte on GitHub. And also, in terms of if you actually want to look and read at these production level compilers that exist, top one is a language called Gleam. Compilers in Rust, so you do need to have a bit of a small understanding of Rust, but it was literally written by one guy who just sat down and just wrote the whole thing. And so, it's not a multi-huge team project and whatnot. You think like .NET could never read the .NET compiler because it's been written by thousands of engineers. It's like if one guy can write a damn compiler, you can read it. Yes, you need to learn a little bit of Rust, but it's not too bad. Again, with the Go compiler, there's those 2 books that like take you through writing the compiler in Go, but the Go compiler itself is also written in Go. So you can look through the source code of that absolutely fine. That's all on GitHub, and you probably won't have any issues reading it. And also, if you are curious and you do want to get into the C# side of it, at the bottom there, you've got the sort of Roslyn compiler. And all of that is underneath there under source compilers, C# portable, and you can find the Lexer, the parser, and so on. I think the only part that's not necessarily in there is the code generation part of it. You might need to do a bit of digging around for that, but it's all mostly under there. And when I was talking before about front ends versus back ends, so obviously in this little project here, this is just a calculator compiler. But what you will find, if it is in here, and it is not, my apologies, I clearly didn't pull before I came to do this talk, but on GitHub, there is a version of that attempts, it still doesn't quite work yet, because for whatever reason I get an exception at runtime, but there is a version of that actually compiles into a .NET executable that you can run. As I say, you get a runtime exception because it's telling me I'm not linking in MS Core lib. And I wish I had it working, but Microsoft changed every single API for generating .NET IL in .NET 9, and I couldn't find an example that would allow me to link it. So I apologize that it's broken. I leave it up as a challenge to yourselves if you want to figure out how to, and if you do, please let me know how, because I've changed all the API. But yeah, there's that idea of, hey, I've done that for my little tiny virtual machine, but I can take that exact same parsing and lexing and all that kind of stuff and use that to compile the .NET. But yeah, that's everything from me. Thank you very much for listening. And does anyone have any questions at all? No? Cool. Well, thank you very much.